Good morning. Thank you to Dr. Leswa for giving us this opportunity to present in front of this highly learned group of people. Dear all, you understand that these days applied science does not work by itself. It actually combines with other disciplines of science to become a formidable, applied science. So in this case, there are three areas of science that we are going to present to you today. Firstly, my presentation is introductory. I am going to give you a perspective from the point of view of a natural science practitioner. So I will enable my other colleagues, the next lecturers, to describe more about the remote sensing technology that actually applies in the area of natural science, more specifically in the area of soil health monitoring. So let's start the presentation. So I'm going to cover Earth observation and soil health, where innovation meets practice. I'm going to include introduction to Earth observation sector, secondly, empirical studies of Earth observation in natural sciences, thirdly, scopes and limitations of using Earth observation technology. So my next lecturer will discuss more about the space science, that means the remote sensing technology. And then the third lecturer will give you an understanding about how the data extracted with the help of remote sensors from natural science are analyzed, and what sort of technology, that means, the artificial intelligence technology and different types of algorithms, how they actually applies. So, thank you very much. Before I go any further, please place your questions through the chat button. We will answer to your questions after all sessions completed, and then we'll have a Q&A session. Thank you again. So I would like to start my presentation with a statement that the agriculture sector is yet to implement remote sensing technologies fully due to knowledge gaps on their efficiency, appropriateness, and techno-economic feasibilities. Now, who made this comment? This comment was made by a group of scientists of Ohio State University. This is what they did to make this statement. They reviewed 3,679 published papers regarding remote sensing technology in agriculture. Those papers were published between 2000 to 2019, and note here, 64% of those papers actually discussed about using satellite imagery. So this statement was made with lots of knowledge, lots of experience. Let me discuss about what is Earth observation. Earth observation is defined as the process of acquiring observations of the Earth's surface and atmosphere by remote sensing instruments. Let us look into this diagram. So these are the four areas of remote sensors. Firstly, handheld remote sensors. Secondly, remote sensors on drone platform. And thirdly, remote sensors from aeroplanes. And last but not the least, the remote sensors from satellite platform. This is quite interesting to see that only 5% of this total, that means the total of Earth observation sector, is from the satellites. So the satellite-based remote sensors only comprise 5% of the total market, whereas we have 1192 EO satellites orbiting the planet. You probably have seen the connection between the first statement and this figure. Let me give you some idea of the past and present of the EO sector. First image of the Earth was taken from space from a V2 rocket in 1946. Ladies and gentlemen, please note the year 1946. That means right after the Second World War. So the V2 rocket has a dark history. It has a blood-stained history. V2 rockets are the first long-range ballistic missiles developed by the Germans. They used these rockets and they killed around 5,000 people around the last part of the Second World War. And not only that, to manufacture the V2 rockets, around 10,000 prisoners of war actually gave their life. So after the World War, the US Army captured some of those V2 rockets. They launched one of those V2 rockets. They attached a video camera to take the image of the planet, and that was the first time the image of the planet was taken from the space. The first successful EO satellite was TRIOS-1, launched on 1st April 1960 by NASA. It provided first TV footage of weather patterns. The use of remote sensing technology in agriculture-related work started with the launch of Landsat multispectral sensors in 1972. Ladies and gentlemen, I hope you can remember that Sputnik was launched around launched in 1957, and the role of the Sputnik was to orbit the planet through the low Earth orbit and just to send a beep signal to the ground station. So in a sense, that was also a remote sensing satellite. From 1960 to 1980, satellites were launched with multispectral sensors using infrared and microwave bands to observe Earth's surface. Let me give you a bit of forecast from a reliable source. There may be 10,000 small satellite launches per year around the end of this decade. Out of that, 20 to 25% could be EO satellites. So, I mean, around 10,000 small satellites will be launched around 1930. So, how about the market? The global market of the Earth observation sector was US dollar 3.58 billion in 2021, and that has jumped. That is predicted to jump more than double around the end of this decade. That could be around 7.88 billion US dollar. The eyes in the sky. The remote sensors look into the planet from the sky, so they are commonly called as the eyes in the sky. So how eyes in the sky observe the Earth? Radiation from the sun falls on Earth's surface, either reflected, transmitted, or absorbed and emitted, interfered by atmospheric constituents and objects. This electromagnetic radiation on interaction subjects to several changes in magnitude, direction, wavelength, polarization, and phase. These changes are detected by remote sensors from satellite platform and that enable to interpret useful information about the object or the target. These remotely sensed useful information contain temporal, that means the amount of time that you take the data. Secondly, the spatial resolution, that means how big is the size of that image. Smallest unit of that spatial dimension is the pixels. And thirdly, the spectral. So the spectral dimension of those data actually means the color, bandwidth, spectral signature, etc. Example, satellite imagery of Sentinel-2. So I'm going to give you an example with the help of Sentinel-2 image data. The Sentinel-2 actually captures the image data in 12 bands. So band 10 usually I'm not going to discuss about, because band 10 only capture the image of clouds. And you can see that some of these bands, these spectral bands, are within the range of our visible capacity, 0.44 micrometer to 7.5 or a little bit more, micrometer. That's the range of our visible light. So that's what we can see with our eye. And rest of the bands we really cannot see with plain eye. Let us continue the example. How we do the labeling and creating training data for land use analysis. What we trained our algorithms with the help of labeling and color coding. As for example, so this is a Sentinel-2 image data. You can see that some area is dark green, some area is bluish. Some of this area, it looks like the roof of houses, and this is probably road. Now, if we want to confirm the ground information, the ground truth, then we have to inspect this area. And with the help of Google, we can actually do a color coding. So when we actually take that color coding into MATLAB, then it looks like this. So this green area is obviously the forest. Let me pick the pointer again. So this green area is definitely the forest. The gray area is actually the housing area, suburban area. The yellow area are the crop fields, and this area obviously a lake or something. So when we do this color coding, and with the help of this color coding, when you train an algorithm, then that algorithm will read any image data and provide us with useful information. Let us see how the reflection band actually moves over the bands of, reflected bands actually moves over the bands of, Sentinel-2. So you can see that the building, trees, roads, water, crops, etc., they all have a specific pattern of reflection. So on band 1, most of this, objects actually starts, and then it goes to the top around band 7, 8, 9, and then it drops down. But the most importantly, each of these objects has very specific pattern of band, reflectance band. We call it the spectral signature. As we actually sign, when you sign a document or something, we try to ensure that our signature will not be replicated. Same thing here, that each of the objects, when they actually reflect the light, that specific pattern is usually not replicated. So that's why we call it spectral signature. Now let's talk about soil health. The term soil health was used since 1990s. That can be defined as the ability of the soil to sustain the productivity, diversity, and environmental services of terrestrial ecosystem. Now, what are the parameters? The US Department of Agriculture, USDA, developed a very specific, straightforward, parameters of, 4 categories. Number 1, soil organic matter. Number 2, physical properties. Number 3, chemical properties. And number 4, biological agents. Just to understand it more clearly, let us make a model with the help of these 4 parameters. It looks like this. So when the bubble of soil physics, soil chemistry, soil biological agent, and soil organic matter joins together, that joining point is the soil health. I hope it makes sense. So, remote sensor and soil health. Let's talk about remote sensor and soil health. Most remote sensors gather information about how soil reflects light. The question actually comes about the reflectance. Mainly in visible 0.4 micrometer to 0.7 micrometer, near infrared 0.7 micrometer to 1.1 micrometer, and short wave infrared 1.1 micrometer to 2.5 micrometer bandwidth or regions. This information helps in predicting physical, chemical, and biological properties of the soil. How? The way plants reflect light can also show soil's water holding capacity, eroded locations, nutrient deficiencies. The band between 8 micrometer to 14 micrometer can help the sensor to capture thermal infrared emission of soil, helping soil temperature related characteristics. So, 0.8 micrometer to 14 micrometer actually capture the thermal infrared emission of the soil. And with the help of that, we can actually understand soil temperature and soil moisture, which is related to soil temperature. Can remote sensor capture possible indicators of soil health? So we discussed about how the remote sensors actually helps to understand soil health. Now let us discuss about specific indicators. Okay, with the help of this diagram, the plants on a soil actually reflects different things. So the symptom of the plant, the phenotypical character of the plant actually explain whether the plant has been attacked by soil-borne disease or pest, whether there is salt in the soil, whether there is high or low pH in the soil, whether there is enough soil moisture, how about the soil temperature, soil aeration, and obviously nutrients, that means fertilizer in the soil. So as natural, science professionals, all of you know that all these factors actually develop certain symptom on the plant. So plant is one of the major indicators to understand the soil health. And when we can actually capture all the information with the help of remote sensors, definitely we can understand the situation of the soil health. Some key findings of contemporary researchers. So one thing I must discuss, dear all, that as practitioners, say we get a project, then we try to find that what our academic colleagues actually resolve that sort of problem through their research or through their experiments. So then we try to take the same practice into practical field. So sometimes we change that, sometimes we customize that to see whether we can actually solve our problem with the help of those findings. So I'm going to give you some key findings of contemporary research. So remote sensors and soil organic matter. Generally, darker soil color is less reflected and represents high soil organic matter content. So you can see there is a positive correlation here. So darker soil, higher soil organic matter content. The spectral reflection band 1.7 micrometer, 2.18 micrometer, 2.31 micrometer are used to predict soil organic matter. By the way, when you see these numbers, these are the references that I have used. At the end of this presentation, I actually included all these references. If you want to continue your reading journey, you can find those papers, and you can read thoroughly those papers to understand it more clearly. So within my 40 minutes time, I'm just going to give you a bit of overview of the whole thing. Thank you very much. Hyperspectral images can enhance the precision of soil organic carbon determination. So now I use the word hyperspectral. So the hyperspectral, I need to explain it to you that this is about the spectral resolution of the satellite image data. So when we talk about spectral data, firstly we consider red, green and blue. Shortly we call it RGB. Then we go on the next step is the multispectral, that means 1 to 100, sort of roughly that range. These bands, some of the bands we can see, some of the bands we cannot see. But in case of hyperspectral bands, we really cannot see those bands in our plain eye. There are several image bands which are captured by the remote sensors, not by plain eyes. Because it is more specific, it can actually collect or study more specific information about the target. So you can see that hyperspectral images can enhance the precision of soil organic carbon determination. Spatiotemporal model, which is nothing but space and time model, also used in monitoring soil organic matter using time series synthetic Landsat image on Google Earth Engine platform. So synthetic Landsat image, what does that mean? The synthetic Landsat image is nothing but computer generated, that means AI generated Landsat image, sort of like simulation of Landsat image. And Google Earth Engine is the cloud platform where lots of image data are analyzed. There are other clouds. I'm going to discuss that later. So Google Earth Engine platform can provide numerous time series satellite images like Landsat, MODIS, Sentinel, etc. Remote sensors and physical properties of soil. Soil color in red, green and blue, as I said before, can be detected within the spectral band of 0.45 to 0.7 micrometer. An increase in particle size results in decrease in reflectance. It's very clear that there is a negative correlation here. That means when the particle size increases, that actually decreases the reflectance. So a spectral band of 0.45 to 2 micrometer helps to determine soil texture. Again, you can see the number here. There is a paper in the reference list. Thermal radiation between 8 to 14 micrometer enables to understand soil moisture, texture, as well as organic matter. Radar remote sensor with microwaves can penetrate the soil surface to some extent and thus help in assessing moisture content, surface roughness, while LiDAR can capture three-dimensional images, helps detecting topography, helps to understand the height of a tree, etc. Remote sensors and chemical properties of soil. 0.4 to 1 micrometer spectral reflectance band can determine iron oxide, while an increase in iron oxide decreases reflectance. Again, we can see a negative correlation here. Similarly, sulfates, carbonates, hydroxyl combination responds at 1 to 2.5 micrometer spectral reflectance bands. Studies were carried out for mapping and monitoring salt-affected soil with mixed results, not 100% clear-cut result. Remote sensing data used in these studies from Landsat, SPOT, IRS, LISS, etc. from these satellites. But Landsat data coupled with machine learning models, so far I know this model is a random forest model, Our third lecturer will give you an understanding about this machine learning models. Anyway, Landsat data coupled with machine learning models resulted wide and best result in detecting soil salinity zones in Bangladesh. So this dot point says that we got a mixed result, and this study got a very clear-cut, understanding about soil salinity zones. Correlation was revealed between relative biomass potential and soil organic carbon. Landsat 4 and Landsat 2 data derived NDVI normalized different vegetation index used in that study. So what is normalized different vegetation index? So I'm going to discuss about vegetation index later. Let me give you an understanding about normalized different vegetation index, which is widely used and very commonly called as NDVI. So NDVI is the ratio between red and infrared values. It is actually used to quantify the vegetation greenness. So how green is the vegetation, and with the help of NDVI we can actually differentiate that. Now, what is vegetation index, plural indices? A vegetation index is a spectral imaging transformation of two or more image bands designed to enhance the contribution of vegetation properties. So with the help of vegetation index, we can understand different vegetation properties. Let me give you an example here. Let me pick a pointer. You can see the movement, the reflection movement of blue, green, red and near infrared is quite uniform. So when the movement, when the reflection is like this, then you can get this color, which is obviously the color of a dead leaf. And then when you get a stressed leaf, then the reflection bands actually move this way. So the blue is short, green is taller, red is short, the near infrared is again high. So this pattern of reflection movement gives us this color. So this is the color of a stressed leaf. And now this is the color of a healthy green leaf, and you can see the pattern of movement of the slides. So this is how the vegetation indices actually can give us useful information. Remote sensors and biological agents of soil. Terra and Aqua satellites data sets in 36 spectral bands helped to understand linkage between below-ground microorganisms and above-ground vegetation. Vegetation indices and multispectral data can enable farmers to identify anomalies, stress in a crop field due to pest and disease, due to microorganisms or invertebrates. Coupling microbial and remote sensing data allow accurate prediction of carbon and nutrient cycle, how the microbiomes react with climate change. So coupling microbial and remote sensing data even helps us to understand how the microbiomes react with climate change. Metabarcoding is another term. I don't know whether you are familiar with. This is about study the leftover DNA and RNA in the soil. It helps us to understand what sort of life forms are living in the soil. With the help of GIS and remote sensors can enable a study microorganisms from its structural, biochemical characteristics of forest like chlorophyll, nitrogen content, canopy cover, height of the trees, etc. Topographical data and remote sensing data integrated into GIS database can help predicting soil biodiversity. Can RS identify anomalies if trained with appropriate data? Yes, it can. Let us see this diagram. This is a potato field. You can see that this particular area has been attacked by some sort of insect pest. This area has been attacked by potato virus. This area attacked by early blight fungus, and these areas are physical anomalies. So, after color coding, if we train the algorithms, then the algorithm will help us to identify these anomalies in a crop field. So this is just an example. So if we train an algorithm with the help of this sort of training data, then the algorithm will identify the anomalies and provide us useful information. I put this cartoon here, soil microbiota. They are saying that we suggest you take us seriously into consideration before messing up with the forest soil. Obviously, no-tillage farming increases soil organic matter and decreases erosion. This is a well-known fact, and this is one of the idea of sustainable agriculture. A few scopes of Earth observation technology today. Near-infrared and thermal data can detect crop stress, hence can be used as symptoms of soil health. Hyperspectral sensors able to discriminate between specific features and objects. I think I have talked about hyperspectral images. Image data over 10 meter spatial resolution are free, provided by Landsat and some other satellites. Dear all, just remember this 10 spatial resolution. That means the pixel size when it is 10 meter. These are free data provided by these satellites, but they are still useful. Tools like TerraLib, Hadoop, GeoSpark, as well as different computer tools like different algorithms, they all work together and provide us different types of useful information when they are trained with big data. The scopes of Earth observation technology we continue. Coupling, customizing, machine learning algorithms and cloud computing enable processing vast amount of remote sensing data. Our second and third lecturer will discuss these things in details. Space LiDAR derived data can provide three-dimensional data like topography. Just to let you know that Spiral Blue, our organization has been working to develop LiDAR sensors that can be installed in the satellites. So far, LiDAR sensors are used on aeroplanes mainly, and recently NASA has installed LiDAR sensor at the bottom of their space station. Space edge computing has enabled small area monitoring achievement. Another achievement of Spiral Blue, we received APRSAF, which is Asia Pacific Regional Space Agency Forum Space Achievement Award for this device. So we actually received a prestigious regional award to develop this device. High-resolution thermal imagery proves useful in detecting temperature difference between soil surface and subsurface of water. Multispectral and hyperspectral data of remote sensor is non-disrupting means of soil health monitoring. Let me give you an understanding about the contemporary trend of research. Firstly, this graph actually gives you an understanding how the recent, the contemporary scientists, they actually pay attention to the platform types. Firstly, the red is satellite, platform. Then the green is aerial platform, and the third one, less important, is unmanned air system platform. And if we go to the next, graph, we can see that multispectral image data actually has got maximum attention of contemporary scientists. And then came the hyperspectral data. And then the red is visual data. So these are the area where the scientists these days actually pay maximum attention in their study. I am almost at the end of my presentation. I'm going to give you some limitations. I would rather call it challenges, and these challenges will be discussed by my next lecturer. I'm just going to give you some generic idea. So limited understanding of the efficiency of remote sensing technologies based on platform type and techno-economic benefits. Limited availability and training of RS-based decision supporting tools. Thirdly, limited interoperability of data and tools from various sources. As I said, the next lecturer will discuss about these challenges in details. So, ladies and gentlemen, I am sort of at the end of my presentation. Your opinion is seriously valuable to us. Please provide your feedback through the chat button. And again, as I promised, I have provided all the references that I used in my presentation over here. So thank you for your patience. Thank you very much. Thank you to Dr. Deswa.